I've deliberately kept it very short so that we have enough time for questions and answers. So I will be sharing with you some of the things that we do here in our road laboratory at Columbia University. I'm very fortunate to have very able collaborators and students, and I'll walk you through some of the different things that we are doing. So Vineet, you can hear me, right?
Yes, we can hear you well, and your screen is visible as well. Yeah.
Okay, wonderful. So let me just tell you a little bit about Columbia University. We are here in heart of Manhattan, New York downtown, and Columbia, of course, is a very rich history with a lot of eminence in the area of medical research. And we are ranked number 3 among all U.S. institutions after Princeton and Harvard. So my talk today is about health, and of course, I mean, we are witnessing some of the health challenges currently in our society with the coronavirus. What I have here are some important statistics that we all are mostly aware of. We know that elders in our society, their numbers are growing. And if I think of, let's say, the next 25 years between 2015 and 2050, this number of 65 years or older is going to grow significantly across the world, across all continents. And old age brings many important issues, and these issues lead them to lose, let's say, work hours. So, for example, people have back pain, neck pain, people fall down, Alzheimer's, or so there are many different, these are the top 10 reasons why people lose work. This is from the World Health Organization. Also today, there are about 1 billion people in the world who need assistive technology. And this assistive technology could be in various forms. People may need prostheses, orthoses, they need wheelchairs, they need mobility aids, they need cognitive aids, or maybe just kind of need simple eyeglasses. And the question that we ask ourselves is, what can we as roboticists do to meet this important need for our society? So this is a quick summary of the kinds of things that we do in our laboratory. And the main idea here is that the brain or the body, we know that we control our movements through actions, which are sort of reflected through our muscle activity. There are various sensors going into the brain. So for example, we have our sensors from the eyes, from your touch, or from your muscle receptors and things like that, and that information is sort of going to the brain, and the brain sort of helps to generate commands for these movements. And we know that there are many people in our society, some old, some young, who may have issues of balance. So for example, somebody with a stroke, somebody with a cerebral palsy, somebody has a spinal cord injury, or they may have movements because of, let's say, a disease like a cerebral palsy, or maybe Down syndrome, or maybe kind of spina bifida and things like that. And they may not be able to have a normal developmental trajectory. And we'll talk a little bit about cerebral palsy in our talk, but more or less I'm going to sort of focus on older people and some of their issues. Now, we also have people who are older, they have balance and falls problem. We know that. We talked about it a little bit earlier on. But in addition to balance problems, they may also have things like neck problem, unable to sort of move their head around. Or many of us spend so many hours on a computer every day, right? And that sort of affects our shoulder area, our neck area, and we look at some of that as well. Also, we know that people have, let's say, a bent spine, sometimes called scoliosis or other forms of it. And the question is, what can we do as roboticists to help this cross-section of people? And And a lot of what the way we kind of approach this problem in our lab is that the brain has the capacity to learn, right? So if you think of an example of somebody, let's say a 5-year-old who's learning to bike, right? And bike, of course, requires you to develop balance, be able to sort of navigate and so forth. And often when we are helping children to learn to bike, we actually put a training wheel on the bicycle, right? And what does the training wheel do? If the child doesn't have a good balance, the training wheel sort of take that slack. And eventually, as the children learn to bike, then you take off the training wheels, right? And then they are able to sort of bike by themselves. So in our lab, we think of robots as training wheels on a bicycle, right? It is there to facilitate or help people learn some skill set, but in the end, they were not going to use those machines or devices, right? So for example, if I think of somebody with a stroke who has temporarily sort of lost that coordination or control, right? The question is, can we use a robot to help them regain their walking function? And eventually then they don't need that exoskeleton, the robot, right? Now, we know that in some diseases or some conditions, it is possible for us to retrain the brain, depending on what is the etiology for that particular disease, right? So for example, somebody with ALS, right, which is, let's say some of you probably remember Stephen Hawking, who was on a wheelchair. The only thing he can do is sit in the chair and use his eyes to control, let's say, things on the machine, right? And for him, there is no way to reverse the neurological deficit or the changes in their muscle activity and things like that, right? So there, the robot is an assistive device as opposed to a training device, right? So in this whole area of rehabilitation, I mean, there are these assistive devices, and then there are these training devices, right? And we have to distinguish between the two. And a lot of what I am going to show you today are training devices, right? But we also work with assistive devices, and it all turns out to be dependent on the way you are controlling the interface of these systems, whether you can tune it to be more rehabilitative or as an assistive device. So in many cases, the technology can be repurposed for either of the two uses. So what I'm going to do here is really kind of focus on a lot of problems in terms of gait, balance, posture in my talk today, and kind of keep the focus over there. So you may be wondering why robotics? I mean, if you injure yourself or somebody has a stroke, of course you go and see a neurologist. You don't come to a roboticist for help. But on the other hand, if you think about some of the recovery processes from these impairments, essentially you design a machine, or you sort of do these rehabilitation by the healthcare workers, or you can use technology as a way to assist or kind of use that as a adjunct to what the, let's say, physical therapists are doing. And of course, I mean, robotics has some very interesting features. You can sense things, you can document it over time, and of course, you can also design these machines in a way that it is according to the way humans learn. And so as long as you promote problem solving and design these things according to motor learning principles, there's a way for you to use these machines in a positive way. Now, robots can also quantify progress, right? So that's something that we talked about. And also, you can ask some very interesting questions. What would happen if I were to create a machine and create this environment for the individual? How would they sort of perform in those environments? And those are kind of exciting for us as roboticists to sort of really look at ways that we can make an impact with machines onto the human movements. So before I go to the elderly, I want to sort of tell you that these things can happen at a very early age. So this was a project that we had for spent about maybe 10 years or so, looking at children and in fact infants, And the question is, can these 6-month-old infants learn to drive a robot? And of course, I mean, you may be asking the question, why is it important for us to have children who are that young look at driving a robot? And you can see in these videos here, these are small children, somewhere between 6 months to about 2 years old. And we are basically saying that even though some of these children cannot crawl or they are just barely able to sit straight, they may be able to actually drive a machine. And part of the motivation here is that we know that the development or the development process of these children require you to have integrate vision, your posture, your spatial awareness. So all of these proprioceptive kinds of things that have to be integrated into your actions. And also these machines allow you to have a social interaction with others. And those are all very important points. And what I'm basically showing you here is that if you work with these children for some years, whether they are developmentally intact or they are sort of development delayed, all of these children are able to use these technologies and be able to integrate that into their environment. And of course, I mean, we have to ask ourselves, how can we sort of integrate some of these children who may be developmentally delayed into the classroom, into the society, into their homes and things like that, so that the mobility impairments that they have doesn't delay their development process. So we had conducted a study with about 50 children when we were at the University of Delaware to see how we could create these mobility for these children. And the idea was to sort of integrate some of this in a classroom. And we know that a classroom is a lot more difficult environment than an empty room. So this was some experiment that we had done in the Early Learning Center at University of Delaware. And you can see that these are kind of complex environments. And those of us who are roboticists, we know that we can have a machine move around in an environment by itself to kind of based on the sensor and the control. But the question is, if we put these children on the machines and have them be able to move around, and in this case these are force reflecting joysticks, and that sort of encodes the information in terms of what direction they push, and if they are not sort of pushing in the right direction, you essentially provide them a feedback with their hand sensor, and eventually these children would learn to kind of drive around. And we had conducted some experiments at that time, and these experiments basically had two groups of people, a control group and a training group, and these are all age-matched children. And what you see here is that early on before the training, neither the control group or the training group can actually manipulate this machine and go to the goal. And so they're pretty much kind of stuck in this first quarter of their maze. But by the end of the training, the group that was trained with a force field, they are able to safely, continuously kind of navigate to the goal. And the children who were not given the force field, they are also able to do that, but not as well as the other ones. And so we use this particular technology to bring these children into classroom. I don't have videos and slides over here, but these are all published papers, and you're welcome to sort of take a look at it, or maybe you can ask more questions at the end of the talk. So let me kind of move on to another topic. We talked about stroke earlier on. We know that there are many people in our society who have got stroke. In fact, this is the 5th largest cause of death, at least in the United States, and I'm sure that it's also there in the rest of the world as well. And we know that people who have got stroke, they have this one-sided weakness, or called hemiparesis, and they also have a lot of asymmetry in their gait, and they have a lack of balance. And these are some sessions that you're seeing here with physical therapists that are kind of very labor-intensive, very time-intensive, and also kind of injures people who are sort of working with them. And so the question is, can we use a machine like this? And this is a machine that we had developed at University of Delaware about maybe 15 years ago. And these are machines that are connected to a walker, which is on a treadmill. And what the machine would do is allow you to apply forces on the foot in order to make the movement. And so many of the stroke patients, for example, you can see one walking over here, and they may have a sort of less ability to move with, let's say in this case, the right leg. And what the machine does is, over a period of time, it sort of challenges them and stretches their gait to see how well they do. So this is a study that we had conducted. This was a multi-session training study with 15 sessions over a 3-month window. And then we looked at the follow-up of these patients 6 months down the road. And what you're seeing here on the right is our exoskeleton called ALEX2. And ALEX is an acronym for Active Leg Exoskeleton. And we had various versions of this. So this is the second version. And later on, we had a third version as well. And what it's really doing is looking at the template of your ankle gait pattern. And over a period of time, the goal is to stretch that ankle pattern from this black trajectory to the green one. And of course, this cannot happen instantaneously, but has to be done slowly over a period of time by challenging them. So here's a video of a stroke patient, and this is a video on the top is early on in the training process, and you can see he has got less confidence on himself. He's kind of holding onto the handrail, and he's walking a lot slowly. His left knee is not sort of moving as fluently. And by the end of training, you can see that he has kind of developed the balance. He's taking bigger stride lengths, a lot more faster speed, and things like that. And there's a detailed study. And in this case, there were 9 patients. So this was really a 3-year-long study in order to look at what is the effect of the gait or ALEX or robotic exoskeleton on the gait of these individuals. Now, this particular plot out here is a pre and post study for this training. And in this case, what you see here on the y-axis is the self-selected speed of walking, not in the machine, but just walking over ground. And we use a camera marker system to record that information. Now, on the x-axis, there are 3 bars. The yellow is the data on an average for these 9 patients here before training. And you see that their average speed of walking is about 0.64 meter per second. Just to contrast it here, a typical healthy subject would walk at about 1.4 meters per second. So they're about maybe 25 to 30% of a normal walking speed of these individuals. So by the end of the training, which is right after the 3 months of training, when they are walking over ground, you can see that their speed is higher on an average compared to your baseline, and that's good. But what is interesting here is that when you brought them back 6 months later on, right, and in those 6 months, they are really not doing it. They're kind of going back to their lifestyle, but we are sort of, our only advice to them that they should kind of go on and walk and use whatever they have gained over a period of time. And what you see here, 6 months later on, their speed of walking is also sort of has increased even beyond the 3-month time window. So this was sort of a great piece of information that with appropriately designed technology and kind of motor learning interfaces, you may be able to increase the coordination and walking speed of these individuals. Now, what you want to sort of see here is that these stroke patients, even after the 6 months, they're at about 0.8 meter per second, right? So that's about maybe 60% of the normal walking speed of a healthy individual. But from a technology point of view, that these technologies could be effective in terms of helping restore gait and coordination. Now, we also found that there are some challenges in this technology, and these machines are, as you can see here, they're very heavy, they're very bulky, they're good for laboratory. And the question is, how do you sort of take this to the home, right? So there are 2 main questions here. How do you reduce the weight of these machines? And secondly, how can you sort of create a technology that could be used in the home environment as opposed to the laboratory environment? And that motivated us to sort of look at alternate technology. And in this case, this is another version of the ALEX, but it's called C-ALEX, or it's a cable-driven active leg exoskeleton. Some of the important features of this device is that this is about 1/10 of the weight of the previous exoskeleton, the Alex. So this is about, say, 3 kilograms as opposed to the Alex, which was about 30 kilograms. And the way we reduce the weight of this machine is by having these cuffs. So there is a pelvic, there's a pelvic cuff, there's a thigh cuff, and then there's a shank cuff. And in between, you have these wires which are kind of routed through these. And these cuffs are actually just 3D printed, and so they're light plastic. And what you see here are some of these wires coming through here, and the motors are essentially kind of placed on a frame around these individuals. And by applying tension in these wires, you are basically coordinating the force that you want to deliver onto the foot. And what we are able to show that even with these kinds of devices, which are very lightweight and were designed really to be wearable and eventually to transfer to people's home, you can actually create those scientific changes in terms of the gait. So these kinds of templates that you saw earlier on, and we did a study first with healthy subjects and then to stroke patients to show that you can actually retrain the gait of these stroke patients. In this case, this was a single session study. It was not a multi-session like in the previous one, but it kind of showed the effectiveness of this idea for stroke patients. Now, another interesting thing that we got inspired with is this picture from a mom helping a child to learn to walk. And often you will see that the moms would help support the child at the pelvis. And pelvis is sort of a very unique part of our body, because what it does is it takes the torso weight, right, and reflects it to the legs, right? So as you are walking, you have your stance phase, you have your swing phase and things like that, and you essentially kind of shift your weight from, let's say, one leg to the other leg during your stance phases or your double support phases. And what the moms was really doing is kind of manipulating the pelvis in order to sort of be able to transfer load. And that motivated us to sort of build this device. We call it a tethered pelvic assist device. In fact, Vineet was the primary researcher who kind of helped develop this particular idea. And what you see here is this little belt. And belt, of course, is only 200 grams or 300 grams belt. So it's kind of very lightweight belt. So that way you're not altering the inertia of the human body. And to this belt, we have a number of these wires. And these wires are essentially connected to motors. And you can reorganize these wires and the motors in different ways depending on what intervention you're doing. You can apply sort of force continuously on the pelvis, or you can intermittently kind of apply. So you can give a short pulse, or you can have a continuous forces. And we work with this particular technology for a number of years, and it's still a very active project for us at the moment. And you can do different very interesting things. And I'm going to show you a few examples with this particular technology. So the first one here is to look at balance and falls. Right, and in this case, what you see here is an individual who's walking on this belt, on this treadmill, and what the machine really does is applies different forces. So these are little short pulses that you provide on the individual. So for example, in this left video, you can see that pulse of force, which drags the person kind of anterior posterior or kind of front and back. While in this right video here, it sort of pulls the person sideways and left to right. And part of the motivation here is that, of course, culturally in different parts of the world, we have exercises, right? People do morning exercises or evening exercises. If you go to China, you have a lot of Tai Chi kinds of things. Or people in India kind of do a lot of yoga and so forth. And the question is, can we sort of improve the balance of people by providing them repeated short pulses, or these we call them as perturbation pulses? And by randomly providing them, we have them experience these instances of falls and see how they recover balance from it. And we have done a number of these experiments, and I'm going to show you one which is for Parkinson patients. And
Dr. Agrawal, just to highlight, the audio is not there in this video.
oh, okay, okay.
Yeah.
Sorry about that. So I didn't know that the audio was not working. So basically it was so basically these are Parkinson patients, and we are helping them to recover or improve their balance through these repeated perturbation. So I'm sorry that the video did not work. I thought that I had clicked the thing to be able to sort of do that. But so I'm going to sort of move through here. But what you're really seeing here is that on this plot over here, these are healthy control, and these are Parkinson patients, and these are age matched, about 65 years old here. So healthy control about 65 years, Parkinson is 65 years. And what you are looking here is this measure on the y-axis, which is called the anterior-posterior margin of stability, and basically where your center of mass is with respect to your base of support, or edges of base of support. And what you see here is the Parkinson patient, of course, have less margin of stability compared to a healthy control. But what is very interesting here is that both Parkinson patients and healthy subjects can improve their balance through this kind of training approach. And that was sort of the important part of it, because many of the Parkinson patients, they actually take a medication that helps in the tremor, but doesn't sort of, there is no solution for balance improvement. So I'm going to move on to another experiment with this T-pad, and these are children with cerebral palsy. And what you see here, this person who's walking, he has a crouch gait, or his knees are not straight, but they are actually flexed. And of course, those are not very good from a walking perspective, because you load your joints abnormally as a result of these. And one of the interventions that we tried out is if we can continuously apply a certain load on these individuals, because we know that when you're walking, you're actually pulling your center of mass or your pelvis up and down while you're walking. And while you're pulling your pelvis up with this external force applied to you, you are hoping to coordinate and strengthen your extensor muscles. And that was sort of the primary hypothesis for this work. And this is just a video of the same individual, and in this case, what you see here, that the child is walking a lot more straighter after the training compared to before the training, and this is overground walking, even though all of the training and everything was done on a machine. And this is a study that involved 5 children and about 15 training sessions, and this was coordinated by one of my students, Jion Kang, who is now a professor at SUNY Buffalo. Now here is what you see in the video of these individuals during the training itself, and this is an early on into the training when the child sort of came to our laboratory, and you can see that he has a very sort of unstable as well as kind of a slow gait, but by the end of training he's walking a lot better, and in fact he's kind of developing the right foot forces, because when you walk you have a heel strike, you have a toe off. And a typical healthy gait is so this is a phase of the gait cycle when your foot is on the ground, and you can see that when you do a heel strike, you kind of generate a big force, and then in the push off, you generate a force. But these children were really not doing this crisply, but by the end of the training, they were able to do that as a result of this particular training. We are following this idea further on, and this is to look at patients with spinal cord injury. And we know that spinal cord injury is a lot more, it's really an episode that happens because of trauma of certain kinds. I mean, you have a car accident and things like that, and you injure a kind of a part of your spine. That means your spine is a highway where you are sending in commands to your muscles as well as the sensor kind of going up to your body or your brain. So now if you break that particular highway, what really happens is that you lose kind of your control. And somebody with a spinal cord injury, they may actually collapse at either the ankle or the knees or the pelvis or the shoulders. So you need really a lot of therapists to be able to do that. And you can see here in this particular picture, this is from one of our collaborators at University of Louisville. And you can see that these two therapists who are sitting down, they are controlling the knees of the individual, while this woman at the back here, she's really controlling the pelvis. And what we are trying to do is to teach these spinal cord injured patients to just, right? So we take standing as granted in our daily life, but here, standing itself is a challenge. So the goal was to sort of be able to replace all of these therapists by a training device or robotic device. And I'll let this particular device play here. But you can see that there are two bells, one at the pelvis, one at the trunk. And what you can really do is you can perturb the person either at the pelvis or the trunk, or you can provide a supporting force at either of the two ends. And using this particular device, we can do a lot of different experiments in terms of balance or how people sort of react to perturbations and things like that. And there is a detailed paper that recently appeared in 2019, which describes this device and its use for spinal cord injured patients. Let me take you to the next slide, where actually I'll show you some videos of real patients with spinal cord injury. Again, you are seeing that these are therapists who are sitting with this individual, right? But now they are not doing the exercises. What the machine is really doing is kind of perturbing them. It's sort of seeing how they react to it, and you can sort of challenge them over a period of time. So this is an ongoing project. I'll let another video play here. This is a second spinal cord injury patient, and she has a different injury. She has a C4 injury compared to this main individual here, who is this AIS is the classification of spinal cord injury. The less, that means they are more injured. For example, your AISB basically means that he's got sort of motor and sensory issues, while the AISD, she's a little bit better than the individual. But in both cases, what we're trying to do is how do you use this machine effectively to help retrain these patients. And in this case, right now, the goal itself is just to have them stand, but then later on it can progress to walking and others. So what we did is we created two stand trainers, one that we use in Columbia University, other one is at University of Louisville. And University of Louisville is the primary site which is doing the clinical experiments, while we at Columbia, we are doing some of the scientific experiment to understand the way the brain and the musculature sort of coordinates and controls movements. So let me sort of walk you through a few more slides here. And this is a work that is a fairly old work here. This is about 2013. So this is something that we had done at All India Institute of Medical Sciences in New Delhi, and what you can see here are Parkinson patients, and she has something called a freezing of gait, and what we had done is to look at kind of design certain shoes that are instrumented with sensors and vibrators, and part of the motivation here was to look at how vibration in the foot synchronized to her gait could improve her gait and balance. In fact, Vineet at that time was a student, and I remember that Vineet was also there in some of these experiments that were done at All India Institute of Sciences at New Delhi. And here you can see that, at least for this particular individual, she had a distinct change in her gait as a result of this vibration therapy. Now, there are lots of interesting things that we are doing in terms of using virtual reality system. And in this case, what we are doing is, as somebody, older person, in this case, she has a lot of ENT issues. So these are kind of balance issues because of your sensory loss. You are not able to kind of vision, or your vestibular information, or your neck information doesn't give you the right yeah. So what we are really doing is have these individuals sort of walk, and in the virtual reality, we program this, and in this case, what she sees is a screen that is sort of oscillating, and you can sort of program the screen oscillation in different direction. And so what we are looking at is, if you perturb the visual field, how does it sort of affect the balance control, right? Because balance control is not just a matter of what you do with your musculature, but also how do you integrate the sensors into your brain. What we could see is that there are people who would respond differently to different perturbations. So in this particular experiment, we were looking at how do your gait parameters such as stride length, stride width change as a result of these various perturbation conditions. So we again kind of did it with able-bodied people, and this was a study that just appeared in the Nature Scientific Reports to look at older people. Now we kind of use this particular technology to see if there were robotic devices that we can use to stabilize gait. So in this case, what this individual is doing, so this is a healthy individual, and we are perturbing the visual field for this individual, and as a result of it, we are kind of generating instability. And what you see here is a robot sort of moving along with us, with her. And what this robot does is provides a light touch to the individual, because we know that touch is something that can improve your balance and your stability. And basically, we did a study where we showed that through the simple light touch, that means so the machine is not providing any force to the individual, but just providing a proprioceptive piece of information as to where the person's body is in space. And what you can see is that you can improve the stability of these individuals. And in fact, I want to sort of say a little bit about a follow-up of this. I could not sort of include a slide in it, but Yogesh at IIT Gandhinagar, along with Vineet and some of his colleagues, so he came and visited us maybe a year and a half ago, and what we did is we created experiments where you have a virtual reality and you are kind of doing catch and throw experiments, and we understand how people sort of adapt their gait parameters to these kinds of tasks. And there was a result that was published in TNSRE last year or so, and maybe Vineet and Yogesh can tell you a little bit more about it. I wasn't able to include a slide here in my talk. So moving on, I want to kind of have this last example or last application, and these are patients with head drop or poor neck control. So I have a video of this lady who is not able to keep her head straight, and part of the reason is that her extensor muscles at the neck are not strong enough to be able to keep her head straight, and so kind of head falls down. And it turns out to be that many patients with ALS, and this is called the amyotrophic lateral sclerosis, and basically all of your muscles sort of decay over a period of time. And as a result of it, they are not able to sort of move any of the part of the body except for the eyes, which they can control towards the end. And so now you can sort of think about is that if you didn't have the ability to control your head or neck, that sort of affects your daily life in so many different activities, whether you are eating food in the morning, or you're taking care of yourself, or you're communicating with others. I mean, your head neck is an important part of that of this series of tasks. And also, as you can expect, if you cannot see somebody eye to eye, that also sort of affects your self-esteem and be able to make a connection with the individual. So what we really did is we created these machines here, and these are really kind of, those of you know, these are parallel actuated robotic devices. So there's a shoulder support, there is a head support, and in between you have different robotic chains. So in this case, this is a RRS chain. So there are 3 RRS chains between your shoulder and your head. And what you're really doing is you can actually show that this is a 3-degree of freedom device, and it was really designed so that way you can move the head, neck in different orientations. So I'll show you some examples of this, but we have published extensively on this particular work. We have used it for a number of different patient groups. As we said, ALS is a very high candidate because many of the patients with ALS, they don't have ability to control their head, neck. And what you can see here in a video, this is an ALS patient, and in this case, the machine interacts with the individual as a way to physically help him coordinate the motion. So on this left here, we are asking the individual to look at an avatar on the screen and mimic the head movement that the subject is seeing. And of course, they don't have the ability because the head would sort of fall down. But on the right video, you can see that with the machine, they're able to sort of make those movements. And right now we have an ongoing project where we want to look at a long-term extensive sort of usage of this particular device in terms of, so even though we know that ALS is not a reversible disease, but on the other hand, this could be a disease where the machine can actually facilitate their movements. So this is my last slide. I want to sort of thank members of our group. We have a very dynamic group of individuals. These are PhDs, postdoctoral researchers, clinical faculty members, and really we have a great environment where we can work with engineers and clinicians in a way that could make a difference to their lives. On this left, you see a video of a mouse, and the mouse actually has a robot arm attached to the wrist. And part of the motivation is to look at how you can sort of create models of recovery, kind of using animal models. And in this case, what we're trying to do is to see if we can facilitate the recovery of, let's say, the cortical or the cortical spinal tracts for these mice, and kind of learn from that to be able to adapt it to the humans, or vice versa, sort of go back and forth between the human and the animals. I want to sort of thank our sponsors, the National Science Foundation, the National Institute of Health, the ALS Association, the Spinal Cord Injury Research Board for many of the things that we are doing here. So let me kind of stop here, and hopefully there's time for questions and answers, and I'm very happy to sort of take those questions as we go along.
Well, thank you, Dr. Agrawal. That was a very informative presentation. I'm sure the attendees will benefit from this talk. And first, I would like to ask the panelist members to proceed with their questions. And in the meantime, the attendees can post their question in the QA box, and then we will take it up to you after the panelists ask the questions.
Can I ask Vineet? Is that okay?
Yeah, please go ahead. Yeah.
Okay, thanks. Great stuff. I mean, really amazing the breadth of everything that your lab has done. Really, really great to see all this. My question is related to the to the stroke work, where the emphasis. I mean, there are two parts to this question. One is the focus on the ankle trajectory, and why the focus on the ankle versus some of the other joints, the hip and the knee, for instance. And the second is, while the kinematics may be improving, I mean, have you had a chance to look at the dynamics and whether sort of interjoint coordination and other dynamic measures also improve when the kinematics improve when you do the rehab?
Mm-hmm. Yeah, thank you, Pratik. Thank you for this great question. And so part of the recovery of the neuromotor system sort of happens. So you have to allow the brain to learn to solve a problem, right? And the problem in this case is that they are not able to coordinate your muscles and your movements. And early on, and so there are a number of these devices. I mean, for example, let's say locomat-like devices where they actually control every joint of the body. But the point is that when we looked at this particular problem about maybe 15 years ago, we wanted to sort of look at the end effector, right? So in this case, that's why we kind of chose the ankle point as opposed to coordinating all of the joints. And when you provide your force at the ankle, so that sort of allows you to sort of vary your joints in more than one ways. That means sort of it gives you that flexibility of being able to choose and learn your path over time, right? So there are devices which are end effector devices versus exoskeletal devices, and we chose to interact with the patient at a force level as opposed to trajectory level, because in fact there are many results out there with locomat-like devices showing that the trajectory control doesn't work. I mean, it may work in the short run, but it doesn't sort of work in the longer run. So that was sort of the motivation for us.
Okay, thanks.
So Vinith, do I go ahead?
Yeah, please go ahead.
So, so regarding Professor Agrawal, first of all, it was a wonderful presentation. I was like, very nice and beautiful work. So few questions are there. Particularly, you are showing the effect of robots being used by children with developmental disorders. So there are two effects, which is the 3D embodiment of the robot, its effect, and the effect how the child is interacting with the robot. So if we dissociate both of them, sort of the 3D embodiment component and the haptic feel of the holding something in the robot. So do you feel which one sort of has greater effect?
So yeah, so I think it's a very a nice question. First of all, I mean these I mean the developments are sort of happening across so many different domains, right? I mean the cognitive domain, your motor domain, and things like that. So the particular experiment, and I probably didn't give enough detail of the experiment itself, but the experiment was designed to see how haptic force feedback, right? So the joystick that the children had, right? What it would do is apply a force on your hand, right? And we basically use an assist as needed strategy. That means we created a little cone, and we said that as long as you are within the cone, the machine really doesn't do it. But if you sort of go beyond that angle that we have for the cone, then you kind of get. So if you are driving in a direction that is sort of taking your machine in the away from your goal, then this force basically cues you to say that you kind of don't go beyond it, or it kind of puts a little force on the hand. And what was very unique in that experiment was what we learned is that just this force cue can actually help you to navigate it, or learn how to navigate, right? So even though I showed you in this maze that was created and with these different compartments and having them to sort of force them to move in different ways. So they learned in that particular maze, but then later on, some of the post-training evaluation that we did was in a different maze. It was a completely different area. So you're not just learning the environment, but you are actually learning that skill set. And that was sort of the focus over there. Now, coming back to the physical embodiment, that is sort of, again, it's a interesting issue. That's something that we did not investigate in that particular work. I mean, how you see yourself to be a part of this environment where the machine and the human are sort of together in that one. And I know that some of your work sort of goes into those kinds of embodiments, and that was something that we did not investigate at that time when we were doing this work. Yeah, okay. But thank you for the question.
Thank you. And one more question is the visuomotor. So you were giving the effect of visual feedback on the balance and gait of an elderly person. It's very interesting. And you were telling, so did you study the visuomotor skill? So when you were disturbing the visual stimulus, of course it was disturbing their balance, and they were coming back, they were trying to adjust or adapt to the variation. But in the process, what happened to the visuomotor skill? So how were they
Yeah.
viewing the stimulus?
So again, this is an ongoing project for us, and if you think about your balance, right? So if you're standing, right, and now and the question is, what sort of contributes to the balance, right? So what you see from your sensors, right, which are your eyes, your ears, your vestibular system, your stress receptors in your body, and that tells you what is your position or configuration relative to your horizontal, right? So for example, if you lean on one side, right, you would know immediately, even if you have eyes closed, that you are kind of leaning on the side. And part of it is happening through your ears. Your kind of ear canals have those sensors, or maybe your receptors on let's say your legs, which tell you that I'm leaning from the side, right? So now think of this way: what if I were to disturb one of those sensors, right? And so that experiment was designed really to kind of disturb the visual piece of it, right? And everything else is intact, and see what is the effect on balance. Now we have done some other experiment. What you do is you keep the vision the same, okay, but you disturb your orientation sense, because it's coming out from the ear canals, right? And see what happens. In fact, we have some other experiments. I didn't sort of go into detail of that, but to see if you were to take one of these sensors at a time and disturb it, right? The third one to do would be that you take a little vibrator and put it on a muscle, right? And now your stretch receptors on the muscle would not know where you are, right? So you kind of disturb the proprioceptive part of it. And so we are basically saying that how do these individual sensory modules sort of affect your balance, right? And now if you think of an older person who falls down, you don't really know why they fall down, right? Because this is really a very complex interconnection of many of these things. And then there are some people who may be more at verge of having a visual being affecting them more than maybe your vestibular, or maybe their proprioceptive, or maybe their muscular, right? So we want to sort of identify or kind of isolate these different components and see where they need help, right? Because if you feel that it's a problem in your visual channel, then that's where they need to go to. I mean, by strengthening their muscular system, you're not going to gain much, right? So this is sort of an identification part of it. In fact, when Yogesh was here with us, we were also kind of doing dual tasking, where the cognitive part was sort of important, right? So while you're walking, you also ask them to do two tasks together and see how does the effect of the two tasks going to affect your gait and balance. So there are so many different ways that you can sort of kind of look at this ability to perform the task, and the scientific experiment has to be sort of cleverly designed, so that way you can sort of take one at a time and be able to sort of understand and be able to say something about it.
Thank you.
Yeah. Thank you, Tuma.
Yeah. If Dr. Agrawal, you have few more minutes, I think some exciting question have come up in the question and answers box. Should we go ahead with few of them?
Yes. I mean, if you do want to just read the question, and I'm happy to.
Yeah. I mean, so Sagar, you are going, or Yogesh?
Okay. So thank you, Dr. Agrawal, for answering these questions. So first question from one of the attendees is, how long after the incidence of stroke were these subjects recruited, and does this period have any effect on the recovery?
This is a great question, and this is I mean, a lot of people have sort of looked at this question. In our experiment, these were chronic stroke patients, so they were 6 months or more after the incidence, right? And part of the reason why we chose these chronic stroke patients, because they are sort of more stable in their life, and we could sort of recruit them and study them. But from a literature point of view, a motor learning literature point of view, if you can bring these training early on in the acute phase of the stroke, that's a lot more desirable. But then that's also challenging in terms of being able to sort of do that, because early on, I mean, they're in the intensive care unit, they're just getting out of it. I mean, that means the amount of work and stuff that you would need to coordinate some of these things is a little bit harder. But there are a number of different studies that have been done where you have acute stroke patients, and the general literature is that if you can intervene at that time, that's a lot more desirable than stroke patient, the chronic stroke stage. So thank you for this question.
All right. So we have another question on the Alex robotic platform, and attendee has asked if you could comment on its origin, success, and challenges. And another participant has asked, is there a scope to broaden the scope from stroke patients to other challenge persons where Alex can be used?
Yeah, so these are all great questions. I mean, when we started on this work in Alex somewhere about 2007 or 8 or so, and we had a 10-year grant from the National Institute of Health to kind of look at this kinds of technologies for stroke improvement. And of course, at that time, the Locomat was sort of the standard in this particular field. And what we were basically finding out is how do you sort of incorporate motor learning paradigms within the training of these stroke patients? And we had a collaborator, John Scholz, who was my sort of clinical colleague who we sort of interacted with. And that's where we kind of used some of the assist as needed, some of the force field ideas, and interacting things at the end effector level. And of course, I mean, those questions of motor learning, of course, kind of exist even in the future and so forth. But one of the challenges is how do you sort of take it to the home environment as opposed to the lab environment? Because we know that especially in these pandemic and so forth, right? People cannot sort of come to the hospital, so you have to sort of bring the technology to their home, and that sort of begs the question: how do you sort of create these technologies that are effective? I mean, first of all, you have to demonstrate that scientifically, and be able to sort of take it to their home, and that sort of and so we have a number of mobile platforms that we are building on right now, and these are sort of taking these technologies from the lab to the home environment. For example, the T-pad technology that you saw in some of my videos. Now they are sort of created on a walker platform as opposed to in a lab environment. And so we would be experimenting that over the coming years or so to see how the delivery of these kind of interventions can be done with those walking platforms. Another question was, could this be used for other patients? So yes, I mean, we designed this Alex 2 as a unilateral device to be used on the weak leg of the individual, but you can also have a bilateral devices. In fact, our Alex 3, if you look into our work, it's really a bilateral device and is designed to sort of have both legs. And maybe patients with MS or muscular, or I mean, there are many other patients who could actually use a bilateral device for a spinal cord injury or muscular dystrophy and things like that. Many of those are bilateral diseases, and you can sort of use it for those patient groups. Thank you for the question, Yogesh.
So the next question is about CLX. There was a screen displayed. So was this screen used for a visual feedback? And if yes, then how does the visual feedback affect the gait adaptation?
That's a very good question. So the feedback is a very important part of motor learning, right? And so you can give different kinds of feedback. Visual feedback is one of them. Haptic feedback, force feedback, right? What the robot is really doing is providing a force on the foot. So that's a haptic feedback. And then you may also have sort of audio feedback. So in fact, we had done a study, I didn't talk about it here, where we look at different feedback and how it affects your gait performance. And so there we compared the visual feedback, the force feedback, and the audio feedback. And by combining them to see how that sort of affects your learning and retention and things like that. So I think the feedback is very important. In fact, in some of our more recent papers, we also had the augmented reality, right? So while you are walking, you actually have a HoloLens, and then you use that to provide sort of augmented reality, right? So because in a virtual reality, you can see your environment as you're walking, but in augmented reality, you can sort of superimpose your environment with what you want to sort of add on to it. So we have several studies that we have done with an augmented reality, and there's published papers as well if you're interested in knowing more about it. Thank you for the question, Yogesh.
All right. Well, Dr. Agrawal, do you have more time to address other questions? We have a couple of them.
I'm okay right now, as long as you all. Yeah.
Okay. So another participant has asked about the light touch gain experiment, and the question is, how is the light touch different from other touches?
So think of this way: if you wake up in the night, right? So and you're trying to find your way around, what do? You kind of sort of really just touch different parts of your room, right? Whether that's a wall, whether it's your desk, your bed, right? And that touch is not really applying a force on you, right? It's a very light touch, right? And what people have shown is that the touch sort of gives you an idea of your sort of orientation in space, right? And so in this experiment, what we did is that if you were to apply a force more than 5 newtons, it will basically buzz, right? So then in that case when you're walking, you would not sort of apply a force more than 5 newtons onto it. And the idea is that, of course, I mean, if you apply a force, I mean, the machine can also apply a force onto it. That has an effect as well, because now what it's doing is it's creating a base of support, right? Which is not just your feet, but also where your mobile robot is, right? So it kind of becomes a triangular base of support as opposed to a kind of a bipedal kind of base of support, right? So here we were only investigating the effect of light touch, because we know in the literature on balance, touch itself can actually give you that sense of orientation. So that was what we investigated in that paper. Yes, thank you, Yogesh.
Thank you, Thank you, Dr. Agrawal. So the next question is, how challenging is it to take these robotic platforms to labs, from the lab to the hospitals, in terms of permissions and certification?
Yeah, so that's a good question. So all of the experiments that you see are really done in engineering campus and medical campus, right? So medical campus is the hospital of Columbia University, right? So we actually have a lab both in the engineering campus and the medical campus. And we would recruit patients either at the medical campus or the engineering campus, depending on what is sort of convenient for this particular patient group. So that's one part of it. So yes, we have to sort of make sure that we do adequate testing on these machines. And so anytime we bring anything to a patient group, we first validate that with able-bodied people to make sure that all of our algorithms are working and things like that. And then we have to go through IRB, which is the Institution Review Board, to make sure that everything is being done ethically and things like that. So that's one part of it. Now, secondly, is how do you sort of take an idea to a market, right? And that's something that I don't focus on myself in the laboratory, because what we do is to look at the science, right, and be able to sort of show that whatever you are hypothesizing is actually met by your experiment and the design of everything that you're saying, right? And we publish all of these in open literature, right? So anybody, and of course, I mean, these technologies are, since we work at the university, so the university sort of own the license of these kinds of technologies. So all of these technologies are available for licensing, right? So anybody in the world can actually license these in collaboration with Columbia University. But my goal, or my laboratory goal, is to understand the science and being able to show that, in fact, these devices have the capability. So in fact, we are just starting out a research, or not a research, this is on children with cerebral palsy, on looking at trunk control. And that's something that I did not talk about out here. But we just got a huge grant from the National Institute of Health. And this is to look at 85 children with cerebral palsy who got a poor trunk control. And we are going to do a randomized clinical trial to show that this idea of, we call it a device, we have a device called Trust, which is a trunk support trainer, to see how effective this kind of technology is with respect to a state-of-the-art technology. So that way we are, so this is a 5-year project for us where we will recruit about 85 children with cerebral palsy, and we will be able to look at a randomized clinical trial to show the effectiveness of this idea. So once we publish that work, right, I mean, the technology is going to be available and anybody in the world can sort of license it. But my goal is to show the scientific demonstration of the principles behind them. Thank you.
All right. We have one more question on how can the researchers actually monitor the recovery of patients?
So yeah, it's a good question. So it all depends on what your research design goals are, right? So when you create a research, you say that here are the outcome measures, here are the post-training evaluations that we want to conduct with them, right? And if your post-training evaluation is to be able to use a camera to sort of look at their everyday life, then that's different. But in most cases, what we do is kind of, we look at bringing them back into our laboratory for one session where we do a lot of these number of evaluations, right? And those are not hard. But on the other hand, if you were to sort of create a technology where you take it to the home environment, right, then there's a need for you to kind of monitor how they are performing the experiment, and then later on, what is the outcome of the experiment. And there are things, there are a lot of ethical challenges in there, right? Because video information or maybe other kinds of information, getting it from their home environment is a lot harder than sort of getting it from a lab kind of environment. So far in none of our projects, we are actually doing things in the home. So in fact, in the ALS project, we are actually going to be spending, or the protocol is that we spend about a day in an ALS patient's home, and where we ask them to do a number of these different experiments, and we do that 3 times over a 3-month period, and then we look at kind of evaluate the outcomes based on that. So it all depends on how you have designed your experiment and what your outcomes that you want to measure, whether it's home or in the clinic.
So another question is, in the force control at the end effector, the exoskeletons can they give joints the freedom to adapt in various ways since the knees are not constrained. So how is it made sure that the participants aren't learning a strategy that might not be optimal?
That's a great question, but it's all about, so if you think of a stroke, let's say as an example, what you want to do is initiate a change in the strategy, right? And it's a very debatable as to how do you sort of initiate this motor learning, or this, I mean, you want to have them solve how they want to move with their leg in a way that is most effective for them, right? And I think it's very hard for us to say that by moving the joints in a particular sort of coordinated way is the right strategy, right? Because everybody is different, right? They're learning how to re-coordinate that gait. And there is a lot of sort of openness in the literature as to how to do this. There is no real one way of doing it. And the goal is to sort of explore different alternatives and see which ones sort of work out. So for example, in the T-pad work, we are only applying a force of the pelvis. We are not really constraining the legs in any way. And in fact, we have another study that we did with stroke patients, and that was a multi-session training study. I did not sort of talk about here, but Vineet, were you involved in that as well with Laurie?
Yeah, I think I was part of that work.
Right. So there we actually showed that through this, just the T-pad, right? So there is no coordination of the leg involved. There's no force of the foot or anything like that. Only thing that we did is that we look at the pelvis, right? And we know that the stroke is an asymmetric gait, right? So there's a weak leg, there's a good leg, right? And the weak leg, normally people don't use it as much. So there is a lot of time asymmetry, right? So they would not sort of put enough weight on the weak leg. They would sort of use the good leg to sort of do most of the walking or most of the activity. So there, what we really did is with the T-pad was we look at the center of pelvis, which is sort of an approximation of center of mass, and we moved it on the weak leg each time the person walked with that weak leg on the stance, right? So think of this way, there's a force that is pulling them every cycle, okay, on the weak leg. And what we found is that they improved their weight bearing, right, and also improved the symmetry of the gait. So there's a published paper in the Journal of Neurological Physical Therapy. So if you're interested, I can send you that particular paper. And so this was only a 5-session training. It was not a long training, so it was a kind of more of a feasibility study. And what we could show is that a group of 10 stroke patients, they actually could improve the gait symmetry. Not substantially, but a little bit of symmetry in terms of their force as well as their gait timing and so forth.
Well, thank you, Dr. Agrawal. We will take one more last question and then we will wrap it. So another attendee asked whether patients with incomplete tetraplegic condition be recruited for gait training using the interventions discussed in this talk.
No, so if somebody cannot ambulate, right, you cannot sort of have them walk with these devices. So one of the preconditions for one of the inclusion criteria in some of these gait training strategies is that they have to be able to walk, right? Maybe not walk very well. So if you remember, we talked about their walking speed, right? Somewhere about 0.6 meter per second compared to, let's say, an average somebody who walks at 1.4 meter per second, right? But so you are walking at, say, 30 or 40% of the typical walking speed, right? But on the other hand, if you cannot walk at all, if you are a wheelchair bound, then you cannot sort of, the device doesn't do that. But we have other projects in our laboratory for people who are who are in wheelchairs. So we have a series of technologies that we have developed for wheelchair users. And these are essentially kind of, spine devices, or they're a belt which is there at the pelvis, and then the other one is at the mid-thoracic and the upper thoracic, and in between you have a robotic device that sort of allows you to sort of do your trunk control and things like that. So there are other technologies that you could do to kind of facilitate whatever they're doing in the wheelchair, but having them walk would be sort of harder. But if you remember our spinal cord injury work, where we're looking at the stand training, there many of these patients would not be able to. So there the goal is to actually having them stand, right? So I mean, but standing is a precursor to walking, right? So that's a bigger change.
All right. Thank you, Dr. Agrawal. It was a very nice question and answer session. And now if I missed anything, any other queries, you may please reach out to us at hcr.lab@itgin.ac.in. I mentioned it in the chat box. Now I would request Dr. Siddharth to conclude the session.
Thank you, Sagar and Yogesh. And thank you so much, Professor Agrawal, for the interesting insight on the human neuromuscular system and how to create new pathways to relearn and restore the functional movements. I hope the participants have also enjoyed the webinar and learned new insights in rehabilitation robotics. Just putting an announcement at the end, we have a second webinar lined up on 29 January. It's by Dr. Ashish Deshpande from the University of Texas at Austin. I request the interested participant to visit our lab website and register for the second webinar of the series. Also, we would like to have a feedback from all the attendees. So please take a moment to fill a feedback form. We will be mailing you shortly. So thank you all for joining us. Take care and see you in the next session. Thanks. Thank you, sir.
Well, thank you, Siddharth. Thank you all. Thank you all for inviting me. It was a pleasure to be a speaker for this event.
Thank you, Professor Agrawal. Thanks, Utma.
Thank you, Dr. Agrawal.
Okay. Bye-bye. Bye-bye.
Thank you.
Bye.
All.
Bye.